Okay, the purpose of this unit is to introduce you to a couple additional op-amp circuits that are very useful building blocks as part of more complex systems. Before we go there, though, I'd like to revisit the assumptions we're making about op-amp circuits when operating in negative feedback, because there are a couple of cases where those assumptions can be violated and are no longer true. So let's first write down the assumptions that we're working with. So the first, of course, is that the current into the op-amp equals 0, or that the input impedance, we'll call Rin, equals infinity. And the second assumption is that there's a virtual short between the non-inverting and the inverting terminals of the op-amp. So these are the two properties that we've been using to solve the circuits that you've seen so far: the unity gain buffer, the non-inverting amplifier, and the inverting amplifier. Let's consider conditions when these assumptions are no longer true. And we'll do this by writing down a few important considerations for when you're designing and building op-amp circuits. The first is that you must ensure that the op-amp always remains within its operating range. That is, the output voltage of the op-amp cannot extend to the positive rail or the negative rail. Because if that's true, what happens is the op-amp is no longer to adjust the output in a way to ensure that there's a virtual short between the two input terminals. So the output must remain between the positive voltage supply and the negative voltage supply. The second assumption that's really important is that the op-amp must be connected with negative feedback. Remember, the goal of the feedback is to monitor the output and adjust the input so as to reduce the errors to 0. So when building your op-amp circuits, make sure that you don't confuse the inverting and the non-inverting terminals of those devices. The third assumption that's important is that this negative feedback must always be present, even at DC. Whoops. So that's one of the reasons why the integrating circuit that you learned about previously was described as a circuit that's not really practical, but that you must turn it into a leaky integrator so that you have a high resistance in the feedback path, because the capacitor in the feedback path at DC would act as an open circuit and would violate this third principle. And the last principle you must always remember is that it's very important never to exceed the maximum differential voltage for an op-amp. Some op-amp circuits, some op-amp devices can have very small limits on the maximum differential voltage between the inverting and the non-inverting terminals. That limit can be as low as a few hundred millivolts, and if you exceed that, you can actually damage or destroy the op-amp. So as long as you're important to take these considerations into mind and never to violate or violate these considerations, our ideal op-amp behavior that we've been using can be assumed to be true. So please keep these in mind as you're designing and building the next circuits.